Hello, students. What we want to do today is look at a new integration technique that involves integrands that we have seen in our previous work. But what we want to do is to be able to apply a technique to integrands that have some modifications that require this new technique. Now, what am I talking about? This is the Weierstrass substitution. So if you remember for your second test, you had expressions, fractions, rational expressions in sine and cosine. And if you were interested in an antiderivative, then you would utilize the conjugate method, just like you were trying to verify an identity in pre-calculus. And you found that by using the conjugation method, that you would produce functions that could be simplified via Pythagorean identities and allow you to rewrite the integrand so that you could find a very straightforward formula for the antiderivative. So that is something that we still want to remember. But with some modifications, for instance, we're thinking when we've got plus or minus 1 as a coefficient of the sine or cosine function, the conjugation method works very nice, very easy, and not very difficult. So what we want to do today is to manufacture a technique which will allow us to say, for instance, if we had a coefficient of 2 for the sine x or cosine x, how could we modify our technique so that we could still compute an antiderivative? And so let's talk about that. I think you might be surprised how straightforward this is, but it is rather unique in the fact that it utilizes an identity from pre-cal. So let me share my screen. What I want to do here is just show you how we can actually manufacture this technique from a half angle identity for tangent. Now, this does not get much play in pre-cal. You may have derived this and conjugated it, but there aren't as many opportunities to use this identity as you've seen maybe the power reducing identities or addition and subtraction formulas. What we want to be able to do is show how this actually does provide a new technique. So again, we'll just assume that our original variable is x. It'll be whatever variable the problem gives us. And so we're going to set u equal to the half angle formula for tangent. But we know from pre-cal that a way of rewriting this particular function is by this fraction, sine x divided by 1 plus cosine x. And so if we think miscellaneous substitution or the second substitution theorem, that means we have to utilize the inverse function. That is the mechanism that allows us to transform the integrand into the new variable and hopefully a simpler integrand that we can analyze. So what we do in this particular case, let's just go ahead and look for the differential. So that's the simplest thing to do first. We'll go ahead and apply the inverse tangent to the first part of the equation here. So x over 2 would just be the inverse tangent of u using the inverse equations. And of course, we remember from our pre-calculus studies that the inverse tangent lies in the interval negative pi over 2 to pi over 2. Of course, as we've done trig integrals and trigonometric substitution, we've had to rely on this to make sure that our arithmetic is correct. So now what we can do, if you see here, we can go ahead and solve for x. So x is just 2 times the inverse tangent of u. And now we can take differentials. We know the derivative of the inverse tangent, so we can do this. So dx would just be 2 divided by 1 plus u squared du. And of course, the 2 just coming from the factor here. So we certainly can't leave that out of the equation. So we have a formula for the differential. Now, as I said before, our integrand will have first powers of sine and cosine possibly, and even maybe a tangent. It just depends on what we're given. So what we want to be able to do is rewrite those functions in terms of the new variable u. So what we can do, and this is very simple technique that you use in pre-calc. So what we can do is just square the equation using the fraction here. So u squared would just be sine squared divided by the quantity 1 plus cosine squared. So again, we're using a technique that you would use in your previous courses, but again, to our advantage, so we can actually solve for cosine. Now, with that said, we can use the Pythagorean identity for sine squared, which is 1 minus cosine squared. And then, of course, factor this difference of two squares as these two factors, 1 minus cosine x times 1 plus cosine x. And of course, that we've got two factors of 1 plus cosine x in the denominator. So one of these will absorb. So that will leave us with u squared is equal to 1 minus cosine x divided by 1 plus cosine x. So very simple algebra, but that's good. This is like, okay, anytime you solve for an inverse function, you were always happy when the object for which you were solving was to the first power and nothing else. That would allow you to get an explicit equation. So we can cross multiply u squared by 1 plus cosine x. That gives us u squared plus u squared times cosine x. So let's remove all of our cosine terms to one side. So we'll transpose this cosine term, and then we'll transpose the u squared term. So that'll give us, in this case, 1 minus u squared on the right-hand side, and then the cosine terms will have the u squared factor and the 1. So we just factor this. And then, of course, the coefficient, so to speak, of cosine x is just u squared plus 1. So we can now divide and have an expression for cosine x, which is 1 minus u squared divided by 1 plus u squared. So the technique here will allow us to produce a rational function in u. And then we can apply partial fractions or some other technique that is already available to us to solve for the antiderivative. So again, the Weierstrass technique, we delay until we've had some practice with partial fractions, because that may be the way to complete the problem if that is necessary at all. Now, you're thinking, what about sine x? We have cosine, and that took a little bit of maneuvering, but now we can have a little bit easier time with sine x. If we go back to the original equation, sine x is just u times the quantity 1 plus cosine x. And so we can write this here and replace the cosine term with the 1 minus u squared divided by 1 plus u squared. So now if we get a common denominator, we'll have 1 plus u squared in the denominator, and now we have 1 plus u squared plus 1 minus u squared in the numerator. And of course, the u squareds absorb. These are gone. And we're left with 2 times u divided by 1 plus u squared. So when we compare this to the differential, we have the factor of u. So these are very closely related. So now we have sine x is 2u divided by 1 plus u squared. Cosine x is 1 minus u squared divided by 1 plus u squared. And then, of course, as we did initially, the differential dx is 2 divided by 1 plus u squared du. Now, of course, if you were thinking about it, you could now go ahead and solve for other trig functions if you ever needed them. So tangent would just be the ratio of sine to cosine, and that would give you 2u divided by 1 plus u squared. So this is usually not what you need to do, but once you have the sine and the cosine, then that opens the door to the remaining if that is required by the problem. You can always rewrite an integrand. As you well know, the trig functions give you so many different forms, and you may spend quite a bit of time trying to show that one form is equivalent to another, as you did in your pre-calculus course when you dealt with proving identities. So none of that has changed, and so this should be just be a walk down memory lane. Now, what I want to do at this point is to cover an example that you might have seen on the last test or seen in a homework problem. And I want to do this method based on how we have been doing it. Now, what you're going to find is if you look in your integral table, this is actually one of the integral formulas. So, and when you look at the actual antiderivative, it is clear that this technique was utilized. So what I want to show you is that reminding you of how you did this before, and then the next example will be utilizing the substitutions that we just derived, okay? Just so you can see the context of this. So if we look at the original problem, we have 1 divided by 1 plus sine 2x. So we've got the first power of the sine in a fraction, okay? And so just to make things simpler and get rid of the 2, we can go ahead and set z equal to 2x. So dz is just 2 dx. So if we do the replacement 2 dx and then 1 plus sine 2x, and then of course adjust for the 2 here with the 1/2, we can now move to the new variable z. So the original integral is just 1/2 the integral dz divided by 1 plus sine z. That you've been doing, no problem. And you're thinking, this sets us up for the conjugate method. Why again is that good? Because we have the coefficient of sine being 1. So that does not offer any difficulty. Again, we'll see in the next problem that does not allow for this technique, why it is important to have the Weierstrass method. So at this point, for instance, if you're on the last test, you just multiply and divide by the conjugate of 1 plus z, which is 1 minus z, okay? So now, of course, in the numerator, we still have the 1/2 exterior to the integral. The numerator, we have 1 minus sine z, but then, of course, we have the difference of 2 squares from the multiplication of the factors in the denominator, which gives us 1 minus sine squared, okay? So that's the key. Then we just go backwards and use the Pythagorean identity, replace 1 minus sine squared with cosine squared. But then we see with the just single term in the denominator, we can break up the fraction into functions that have fairly simple antiderivatives. So now we just have 1 divided by cosine squared, which is secant squared. And then, of course, we have sine divided by 2 copies of cosine. So sine over cosine will give us tangent, and 1 over cosine will give us secant. So we can just write minus secant times tangent. But of course, these are simple derivative formulas. We know that the derivative of tangent is secant squared, so its antiderivative is just tangent z. And of course, the derivative of secant is secant tangent. So this antiderivative is just secant. So this is what you'll see in the integral table. And again, even if you didn't use your integral table, you would be okay doing this. This is a common technique. You learn about this in Calculus 1, and it's very useful. So if we look at this, the only thing we need to do is just do the replacement. We know z is 2z, so we have our antiderivative, or the most general, is 1/2 times the quantity tangent 2x minus secant 2x plus an arbitrary constant. Now, you might be thinking, if we used a different technique, the form of the antiderivative will most likely or necessarily look different. And many times students are perplexed by that, because it's like if you use a reduction formula or use a power reducing identity to do a trig integral, the antiderivatives look very different. And it's very time consuming to show that those particular functions differ by a constant. Sometimes it's just easier just to verify that when you differentiate them, you get the integrand. But that's what we know from the mean value theorem. So don't be surprised, again, if you use a different technique, that the actual antiderivatives look quite different. We know this also happens with logarithms, so be ready for that. So let's look at this. So now what I'm going to do is I'm going to rephrase the problem with the Weierstrass technique. And this looks very different, doesn't it? Okay, so I'm going to adopt the same procedure that we had before. That is, we have the dx divided by 1 plus sine 2x. I'm going to do the same substitution here and just say z is equal to 2x, dz is 2dx. So this looks just like the last problem. And so now, of course, this is exactly what we had before. So there's no difference at this point. So what I want to do, or what I want to show you is, since we have the Weierstrass technique, let's go ahead and use that just to get some practice with it. Now, remember, with the Weierstrass technique, we know u is tangent of z over 2. We just use the variable from our formula, from our integral. Sine z is 2u, over 1 plus u squared. And dz is just 2 du over 1 plus u squared. We don't need any other trig function, so this will suffice. So what we see now is we have the second substitution theorem, the miscellaneous substitution. So dx, we just replace that with 2 du divided by 1 plus u squared. And then the 1 plus sine, well, let me go over here. 1 plus sine z, we'll just have 1 plus 2u over 1 plus u squared. So you can see that this is a very straightforward process, and it requires just fractional algebra. So we need a common denominator, which is 1 plus u squared. So that's going to give us a 1 plus a u squared plus 2u, which I just write in descending order. And then, of course, the 1 plus u squares will absorb, and the 2's will absorb. And that leaves us with a very, very simple integrand, because the u squared plus 2u plus 1 is a perfect square. Now, just because we can use the conjugate method, you're thinking that's the reason, this is going to be a lot simpler. Well, maybe. And in most cases where you don't need a more strong or just a more elaborate technique, you're thinking, is it overkill to do it? Should I just stick with what I know works? Well, what does your professor always say? If you have a new technique, practice it. Just get more familiar with it. So it'll be part of the lexicon that you use when you do your antiderivatives. So now we're like, well, we love these kinds of integrals. This is just the power rule, add 1, divide by the new power. But of course, I'll write it in a more user-friendly form, which is just the quantity u plus 1 to the negative 2 power. So again, power rule gives us u plus 1 to the negative 1 divided by negative 1. We love it. We don't even have to do any adjustment here. This is table ready. And then, of course, we can just write this without the negative power is negative 1 divided by u plus 1 plus an arbitrary constant. Now, we need to go back to the original variable. We know that u is tangent, in this case, of z over 2, which we have here. But if we go back to our original substitution, x is just z over 2. So now we can just replace the z over 2 with x, and we have our original variable. So now we have an antiderivative, which is negative 1 divided by 1 plus tangent x, and the family of antiderivatives, adding the arbitrary constant. So now when we compare the two antiderivatives, this looks very different. This is not surprising. So what I want to suggest to you is that this is not an overly difficult technique. It just looks different. It's very new, but it should remind you of the trigonometric substitution, which again utilizes the second substitution theorem. So maybe this is not something you will remember, because maybe you won't use it as much, but it is very effective when it works. Now, what I want to do is show you an example of where we would need to use this technique where the conjugate method would not work. So now let's look at this example and compare it to what we would normally think of doing when we have the single powers of trig functions, sine and cosine or whatever, in a fraction. Well, when we look at this, and I just thought, well, I'll just go ahead and use some basic polynomial long division, so to speak. So we have the 2 sine x in the numerator, and we have the minus 3 sine x plus a 1. Now, of course, if we're thinking conjugate method, we hit a snag here with the -3. Again, that's where we have the problem trying to assign the Pythagorean identity, because we've got coefficients that don't mesh with that. It's not like we're doing the trig substitution where we can adjust for that. So this is a case where we would need to utilize the new technique. So what I just did the polynomial long division. When you divide the -3 sin x into the 2 sin x, you'll just get a -2/3. And then, of course, when we multiply, these two absorb, but we're left with a -2/3. And of course, when we subtract, we just get 2/3 here. So now we can rewrite the integrand as what? -2/3 plus, again, the division algorithm, plus 2/3 divided by 1 minus 3 sin x. Now, this cuts down on the number of instances of the trig function. Now, of course, if you have a cosine, then you've got to use the 1 minus u squared divided by 1 plus u squared. So just remember, you only use the formulas that you need or that are required by the problem. So now I just remind you, we've got our original variable here as x. So we have u is the half angle formula here with the tangent. So we get tangent of x over 2. Just reminding you, dx is 2 divided by 1 plus u squared du, and sin x is just 2u divided by 1 plus u squared. Feel free to put these Weierstrass formulas on a page that you have for your integral table, because this is just a technique, and it'd be like having a little addendum on your integral table sheets to provide this technique. So that would be fine to include. So now we look at this, and I've just noticed, well, of course, -2/3 is a simple antiderivative. We just dispose of that and just drag it along, unfortunately. But here I've got written in red, use Weierstrass. So we do this, we proceed like we did with the last problem, but we're anticipating that there'll be a little bit more work involved because the conjugation method didn't work or would not work in this case. So what we have here, we just do the replacement for the dx, which is 2 du over 1 plus u squared. So very similar to the last problem, once we do the reduction. You don't have to do this, you just have a whole lot more algebra if you don't. So I tried to make this look like the last problem so that we have some confidence in doing it. And so now we have the -3 times the sin x. So we just basically get a -6u divided by 1 plus u squared, which we have here. Just like the last problem. And again, don't anticipate any algebra in these problems. Just do whatever is required by the form of the integrand, and it will change with every problem. So now we just get a common denominator of 1 plus u squared. So we'll have what? The 1 plus u squared minus the 6u, which here I've written in descending order. And now, of course, just to make things a little bit simpler, you notice I factored the 2/3. And of course, now the 1 plus u squared is absorbed. So we're left with something that we are actually quite familiar with. Now, another thing with the 2 here, if you want to just go ahead and discard that or just move it out using linearity, we'll have the 2 times the 2/3. Of course, we can't discard it. We just kind of push it to the side and don't forget it. So now, if you remember, on the first day, we did this derivation. We had the derivation for the reciprocal of the quadratic function, and we utilized the formula that we got from the inverse hyperbolic tangent. And also, when you think about it, the other form had to do with the inverse tangent. That is, we have inverse tangent and inverse hyperbolic tangent coming into play, depending on the sign of the discriminant. So what I did, instead of using that formula, which you had to use on the first test, I thought we might just go ahead and complete the square and use our inverse hyperbolic form that we're very familiar with, just to get some extra practice. So what I've done here, we complete the square, it's already monic. So notice if we take half of -6 and square it, we get a 9. So we add and subtract 9, not forgetting the 1 here. So that leaves us with, well, the perfect square and a -9 plus a 1. So we have upon completing the square, we have the quantity u minus 3 squared minus an 8. Now, what I did here, I put a box around this formula that we use often. And so we don't have to, do too much moving around as far as negatives here. What I decided to do was go ahead and factor the negative here. So we have the negative 2/3 x minus 4/3, where I flip this around. So we have the a squared term first. We write this down so many times, it's so simple. Now notice I did not use the same variable u since we're already using that. So I just have an omega here. And this is the form that we've become very familiar with. It turns up quite often in our calculus study and in physics. So it's one of our friends. So what we do in this particular case, we think about this. What do we need to do? Well, notice omega is just u minus 3. So we've got table ready when we think about differentials. And then, of course, if a squared is 8, a is just the square root of 8. So we can apply this formula directly. So we're going to need a plus omega and a minus omega. So now we've got our negative 4/3, and we have 1/2. We have the factor 1/2, and then, of course, the factor 1/8, which we have is 1/2 root 8. Now we just fill everything in. We have a plus omega. So this will be the square root of 8 plus u minus 3. And then with the minus, we just run the minus through. That'll give us a minus u plus a 3 downstairs in the absolute values. Now, if you like, and it doesn't matter, there's absolutely nothing wrong with this. But if you like, we can go ahead and move the negative upstairs and get it out of the way. Notice the 8 is just 2 root 2, so that'll give us a 4 root 2. So the 4s will absorb. And then if we run the negative up, we just flip the fraction. And then, of course, the u is the half angle formula for tangent. So we have square root of 8 minus tangent of x over 2 plus 3 divided by the square root of 8 plus tangent of x over 2 minus 3 plus the constant. And then, of course, here, I just go ahead and write this absorbing the 4s, and we have a factor of 1/3 times square root of 2 before the log term here, and then just restating this. So what you're seeing here is a situation where if we use the Weierstrass substitution in a particular problem where it is required, we're going to get usually a more complicated integrand. Now you're thinking, do we have to just kind of settle with the half angle formula for tangent? Of course not. You could just rewrite it as the sine x divided by 1 plus cosine x, but this is more than sufficient. Lots of times students are surprised by this. Again, we should not be surprised because we are developing this technique based upon the half angle formula for tangent. So as you do your problems, do what we've done here in this lecture. That is, if the conjugate method will work, apply it, and then practice with the Weierstrass and compare the quality of the antiderivatives. But just remember, this is fairly easy to spot when you have the first powers of sine and cosine, and you've got coefficients other than plus and minus 1. You really do have to look for another technique. So the Weierstrass is very useful and quite ingenious when you think about it, just using a half angle formula to open the door to a method for determining an antiderivative. So I hope you enjoy using this. I think it'll be a lot of fun, just like doing trig substitution. And we are done.